Good. Yes, thank you so much. Hello also from my side. So my name is Corina. I'm product manager at the company MBV. We are based in Switzerland, okay, and we are manufacturer of air sampling solutions for clean rooms. And the topic today I'm going to talk about is how to assess the quality of such an air sampling device. So maybe it's the yellow one on top left you're using, or the squarish one, the white one on bottom left, or maybe even the modern silver one in the middle. Your trustworthy partner for your daily active environmental air monitoring in the clean room. But let's be honest with each other. Who of you has ever been wondering how good this air sampler really is? That's the topic of my talk today, and we are going to look at several aspects to answer this question. But let's first look at the requirements that such an air sampler needs to fulfill. So first of all, it's about compliance. To be 100% compliant with all the regulatory requirements. This is a necessity and not up to negotiation. Then it's about reliability of such an instrument. This is important because otherwise we will not get reproducible sampling results. And ultimately, you want to increase the safety of the end products you're producing. And there I see two relevant aspects. First of all, the collection efficiency that needs to be high to have representative sampling results. And then, on the other hand, it's about isokinetic sampling. This is important to maintain the laminar airflow in the clean room. Let's first dive a bit deeper into the regulations, the more boring but very important part. So what I show you now is a list of all relevant guidelines in this context. I'd like to point out the list is not complete, but it gives you a broad overview. And the first three are of explicit importance. So the ISO 14698, which is the biocontamination control for clean rooms and associated controlled environments. Also the EN 17141, which has replaced the first one in Europe. And then of course GMP Annex 1. Everyone is talking about it, and it's also very important for microbial air monitoring. I suggest, or I recommend you to look into the first ones, especially because it's the only document that actively compares those two sampling methods. So passive sampling, where you use a sedimentation plate, versus active sampling, where you use this air sampling device. It's also the relevant documentation when it's about validation. So these guidelines define how to validate your air sampler. And then GMP Annex 1. So I said before, everyone is talking about it, about how to implement the requirements of the revised version. And also for microbial air sampling, I see 5 relevant pillars here. So first of all, paragraph 931, where it's about the identification of the microorganisms down to species level. Then we have the topic of continuous viable air monitoring, especially in the very critical zones, so grade A and surrounding B. And here paragraph 924 mentions that it's allowed to combine active and passive methods to achieve this. Then we have the topic that absolutely no growth is tolerated in grade A. And whenever there is a rise in the level of contamination, this needs to follow an investigation. As well, It's relevant to show supporting data for the recovery of the chosen sampling methods. And whenever possible, paragraph 928 says that you should consider to implement rapid methods. Why? Because with this you can speed up the time until you find the decontamination. So our air samplers, MAS 100 air samplers, they comply with these deliverables here. If you want to know more, just follow the link that I show here, which is a white paper and gives an overview. The second aspect I mentioned in the beginning, apart from the regulations, was the reliability. So let's look into this topic. So here, it's mainly about validation of such an air sampler. And this is largely in the hands of the manufacturer of such a device. What is in the focus? So the guidelines are defined by the ISO 14698 and the EN 17141 I mentioned in the beginning. And what is in the focus there is the determination of this physical and biological collection efficiency. So this is usually done by the manufacturer externally in a lab to have independent data. And when then the instrument is handed over to the customer, it's more about the qualification part, because then it's about ensuring over a longer time frame that this instrument still fulfills the specifications. And then you do regular recalibration of such an instrument. Let's dive a bit deeper in the topic of the collection efficiency, because it's so important for the validation. There are two different types of sampling efficiency, the physical and the biological. Why is this efficiency of this high importance? So imagine being in a clean room where you have a certain level of contamination. You want to have a true image of this contamination in the clean room. That's why your sampler should have the highest possible sampling efficiency, to have representative samplings in the end. So physical efficiency, on one hand, says how well this air sampler is able to collect those particles on the agar plate. It's a complicated formula. It's depending on the particle sizes of those aerosols and on the geometry and the airflow volume achieved by the air sampler. In general, we can say the higher the impaction velocity that the sampler can achieve, the higher the physical efficiency. And then, on the other hand, we have the biological efficiency. This value then says how many of those particles you sampled are in the end still viable and can grow on the agar plate, forming colony-forming units, which you afterwards can count. This efficiency depends very much on the type of microorganism. So not every microorganism has the same resistancy towards the external forces that come with this sampling. So it's the way, so we can say in general that the higher the impaction speed that the sampler can achieve, also the higher the risk these microorganisms can get damaged, which we want to avoid. So you see already a bit what I'd like to point out. In the end, you cannot maximize both efficiencies. So a sampler is always a compromise between those two efficiencies. The physical efficiency can be calculated with this D50 value. It's also called the separation efficiency. And it says at what particle size the sampler is able to still sample or collect 50% of a particular particle size. It's a complicated formula, that's why I don't show it here, but to give you an overview, it integrated in the formula is a factor for the air viscosity as well as for the particle density. Then it's about the diameter of the openings of such a lid, and of course the air volume flow that the instrument can achieve. So the D50 value can be visualized very nicely. I show you a curve here now for an MAS 100 sampler. So what you do is you plot the different particle sizes versus the impaction efficiency. And what you get is an S-curve, and this is the one for the MAS 100 NT. And the D50 for this instrument is 1.1 micrometer. So what does this mean? Let's look into this curve. So on the left side, so for particle sizes lower than 1.1 micrometer, we have rather low efficiencies. You see it, the curve rises only below 50%. And then we have an inflection point here with the 1.1 micrometer, and every size above here has a higher efficiency. With 2 micrometer for this specific air sampler, we have a saturation point where we have almost 100% reached. In the clean room, we are facing particularly larger particles. And that's because microorganisms, they tend to not come alone. Sometimes they come in groups, or sometimes they stick, for example, to a skin flakes, which makes their total size bigger. So that's also why the regulations see a D50 value of lower than 2 micrometer as appropriate, to be sure to really collect those larger particles with a high efficiency. This was a rather theoretical discussion now, but of course you can also measure this D50 value experimentally. So let's look into this. This is done using a spinning top aerosol generator. It's a device with which you can produce aerosols of a wanted size, let's put it that way. And those aerosols, they contain sporicides of the different sizes. And what you then do is you measure with a test device and a reference device, and by comparing or setting these values into relation, you get the physical efficiency curve for your dedicated test sampler. Again, we are talking in this case about the MAS 100 NT. The curve looks the following. So what we can read out of the curve is that the lowest possible particle size we can measure is around 0.8 micrometer. For this particle size, we have a recovery rate of higher than 50%. So this means that the experimental D50 value for this sampler is even below the 1.1 we have calculated before. You may ask yourself now, why do those two values, why are they not similar? I see there two aspects. So first of all, the curve before we have seen was calculated. And here in this is really experimentally, so we are dealing with viable microorganisms, and that's why this is the much more true image. And then I see the edge effect. This is a physical effect which is affecting the size of the openings of such a lid. It can be a hole as shown here, or it can also be a slit. And this edge effect makes the opening size artificially smaller, and therefore increases the speed and also the efficiency. This can be an explanation for this lower experimental D50 value. Let's now look at the biological efficiency, the second one we have talked about. So to understand damage of microorganisms, we first have to look into the physics of the impaction. I show you here on the left an image from the publication of Stewart. And what it shows is an opening. So could be, for example, one of those holes here. And then here we have the agar plate. And also what is shown is the trajectory, the air trajectory, and the microorganism, which is the black dot here. And what we see are 3 different images with different impaction speeds. I think it's much easier to explain this concept with an analogy. So let's assume you are sitting in a car. You're sitting in a car and want to drive through this opening and get this curve here. In the first image A, because you're driving so slowly, you can easily do that. You can perfectly navigate your car. You will not touch the wall. You will stay on this line you want. Then in figure B, if you're increasing your speed, you drive much faster, then you tend to get some problems, as you see here with this curve. There is a high probability that you will scratch your car, you will maybe even stick to the wall, like the microorganism in this case. And then with image C here, where you have full speed, there is no chance for you. So you will almost directly drive towards the wall, you will crash with the wall, you will certainly not wake up the next day, similar as the microorganism might feel in this context. So the relationship between the size of the impaction speed here and the collection, recovery, or damage of such a microorganism was studied by Stewart. And what he has done is he has looked into a specific range, so between 24 and 250 meter per second impaction velocity. And he has done this for different microorganisms. And what we see here are 2 plots. So on top we have P fluorescence, which is a much more resistant term and has the inflection point at around 40 meters per second. And then we have Micrococcus luteus on the bottom, which is more sensitive. There we see the inflection point at 24 meters per second. So coming from this data, it's suggested that air samplers have an impaction velocity lower than 30 meters per second. And what we see with the blue line here is again specifically for the MAS 100 air samplers. There we have this 300 times 300 holes times 0.6 millimeter size. And there we reach an impaction velocity of 19.7 meters per second. So we are totally in this range that is suggested. The biological efficiency can, of course, also be studied experimentally. So let's look into this. It's usually done in a chamber with a collision nebulizer, so a device that produces aerosols. And what you do is you have a bacterial suspension, and you have 2 types in this suspension. So usually a much more resistant form of a bacteria in a sporicidal form as your reference germ. And then on the other hand, you have your test germ, which is in its native biological form. And what you then do is you sample with a test device, with a reference device, and by setting the values into correlation, you then get your biological efficiency for your test sampler. What we see here on the left is the biological efficiency for the MAS 100 instruments as an example. It's around 78%. Guidelines suggest to have 100 plus minus 50% as acceptable. Now, this efficiency topic we talked about depends heavily on the perforated, or on the lid which is used. And what is known is that the precision of each of these openings is very crucial. So every opening should have exactly the same size. If this is not the case, you will have different speeds in the different openings, and you will not have a very directed airstream, and therefore no representative sampling. This we want to avoid. But now we asked ourselves, what actually about the lid design? Because on the market, there are no regulations or requirements regarding the lid design. So we, as MBV, for example, we have lids with holes. But there are, of course, other manufacturers. They might have slits, for example. So what is the impact of this lid design? And this is why we did a study. We set up a study to compare this. And what we have done is that we used our classical hole lid that our instruments use, and two different slit designs here. So both had 20 slits. One had a size, an opening size of 1.2 millimeter width, and the other one of 0.3, and the needed length for the different slits. And what we have done is a randomized setup, so we have changed the positions, and the sample size was 30 per lid type, and we have done this in an unclassified area. Because we wanted to be absolutely sure to have enough CFU counts then on the plate for doing the statistics. We have sampled 200 liters of air in each case. And now I'd like to show you the results. So it's this plot here on the left. You see the mean values of the CFU counts shown on the left for the whole lid, and then in the middle and on the right for the two slit types. What we have found out is that we had a significant higher CFU count for the whole lid compared to both slit lid types. And we of course asked ourselves, why is that? So we have looked into different physical as well as biological effects that are relevant in this context. And with the study, we have found out that it was not the physical, but rather the biological effects that were able to explain this significance here. The details of this study can be read in the white paper we have with us. I have it here, but I'm also happy to share with you afterwards at our booth. The second aspect we mentioned in the beginning for representative sampling results was isokinetic. Let's dive a bit deeper in this topic. So why is it important? We want to give every particle size the same probability to be sampled on the agar plate. That's why isokinetics is of crucial importance. So what does it mean? So first of all, the sampler needs to be placed in the same direction as the laminar flow that is provided in the room. Usually this is vertically, so place your air sampler vertically. And then it's important that the instrument sucks air with the same airspeed as the laminar airflow in the surrounding, because then you are measuring isokinetically, as shown here on the left image. If you change the speed, then you change the behavior. Let's look into this. So with the middle image here, it's the case of hypokinetic sampling, which means that the sampler is sucking less air than is provided by the room. This is problematic because we have, with hypokinetic sampling, a statistical oversampling of larger particles. Why is that? Imagine a larger particle is on its way here on this blue airflow, this air trajectory here, and it actually wants to follow this path here. But because of his high mass inertia, it will not be able to have this rapid change in direction. Rather, it will fall onto the plate and be sampled. It's critical because hypokinetic sampling increases your risk to have false positive results. You want to avoid that. On the other hand, we have hyperkinetic sampling. In this case, the sampler draws in more air than is provided by the surrounding. Similar here, we have something we don't want, so a statistical oversampling of the undersampling of the large particles. Again here, a larger particle is on its way. It should make this rapid change in direction. It will not be able to do that, again, because of the mass inertia, and will miss the agar plate. So you have a higher risk to have false negative results. This is especially crucial because with this you can oversee a contamination in your room. I would like to point out that isokinetic doesn't stop here with what's happening before the agar plate, so it's also relevant how the air exhausts the instrument. So again, in our room, in our clean room, where the air is coming in a vertical laminar airflow, you should make sure that your air of the sampler exhausts in the same direction. Isokinetics can also be studied experimentally. I show you here data we have collected for an MAS 100 instrument with such a lid, which is optimized for 100 liter per minute airflow. On the left, we see computational fluid dynamics simulation, and on the right, visualization with real air, and we can look into this. So the image on the left here, 100 liter per minute, it shows you with the color pattern. So red are very low velocities, and the more green and blue it gets, the higher the velocity. We see with this color distribution here that we have absolutely no disturbance introduced to the laminar airflow. This is further underlined when we look at the air visualization. Here you see it's perfectly undisturbed, even though we suck in air here with 100 liter per minute speed. But if we change this airflow speed, for example, to 25 liter per minute in this case, the dynamics look different. So we have more yellow and especially red velocities here, as shown by the color scheme, which means that the air is slower, it's slowed down. So we are introducing air turbulence, and we are not collecting isokinetically here anymore. And for this particular airflow, this head would need to be adjusted. This already brings me to my summary. So let's summarize again what is important for microbial air samplers. First of all, compliance with regulations. And then we recommend that you search for a trusted supplier that provides you with external data for the validation and helps you to qualify your air sampler on site. And then it's about representative sampling results and the two aspects that are important. So a collection efficiency that is as high as possible without damaging the microorganisms. Keep in mind the lid design there, and as well isokinetic sampling to maintain the laminar airflow in the clean room. If you stick to those points, you will gain security and control over your daily environmental air sampling process. I thank you very much for your attention. I'd like to mention that we have a booth. It's C9, so if you want to meet myself and my Swiss colleagues, then you're happily invited to come there. Also to discuss topics in more detail and to provide you with those documents about the study, slit versus hole, and the isokinetics. We would like to use a little bit of our time for a little surprise. We have brought an exclusive market introduction today that we would like to share with you, and I'd like to welcome my colleague Roland on the stage to talk about our newest innovation.
Sorry for the hijack, we don't usually do that, but we also do not have very frequently world's first product on the market, so there is something that has that's to our attention not available. Corina has talked today about active air sampling technologies and what to look for. However, extremely many people actually use passive air sampling, saddle plate air sampling, and that is a process that is super manual. Everyone has to do sampling, plate change every couple of hours in an isolator or also in a clean room. And we have been requested by GMP Annex 1 to use more automated technologies and to take out manual interventions in clean environments. And so we have developed on customers' request an automated sample plate handler, which is on display this morning, first time ever worldwide for 2 hours now. So if you would join us later at our booth and have a look, we would be really pleased to show you how it works and what it can do. And sorry for this quick interruption. I'm sure Corina has many questions that she can answer for you.
Corina, Roland, thank you very much. Roland has rapidly run away, so questions only for Corina. Does anybody have any questions you would like from the floor?
Gordon Farquharson, thank you, Corina. I want to go back to your isokinetic sampling.
Yeah.
In the new ISO technical report, which we're going to hear about, I think, tomorrow, part 21, there is a discussion about isokinetic sampling for airborne particles in particle counters and the tolerance for different unidirectional airflow velocities. So 0.45 is the old magic number that goes back to the 1950s. And today we see very often in isolators much lower velocities. Do you change your inlet volume for different unidirectional airflow velocities, or have you done work to indicate that the over and under sampling that you talked about due to velocity differential you can tolerate it? That the uncertainty of measurement in your microbiological sampling is acceptable for different unidirectional airflow velocities?
Is it? I don't know. Yes, thank you for this comment. So the data I have shown here is actually really it lays back to the old historical number of the 0.45 meters per second. So with the speeds you mentioned, we need to look into this to provide data to show it. Yes, I don't have it with me now, but we can do that. Yeah.
Yeah, it's an important watch point as we start to change what we consider to be an acceptable airflow velocity inside our unidirectional flow devices. They are changing from what we set as 0.45 meters per second plus minus 20%. I was doing a calculation as well, thinking about microbiology and these bugs that we're trying to collect with good efficiency, and they accelerate from what we call unidirectional airflow or laminar flow into this sampler at 30 meters a second. I just sat in the front calculating that. That's 67 miles per hour, or more than 100 kilometers an hour. So we accelerate these bugs from unidirectional airflow at 0.3, 0.4, 0.5 meters per second up to 100 kilometers an hour and slam them onto this agar plate. So the biological efficiency is really, really important if we're going to recover and resuscitate these bugs. Any other questions from the floor for Karina on microbiological air sampling?
Hi, Kevin Smith, IPS. I have a really stupid question, but I have to ask it. You put up a chart there about the MAS 100 and compliance with, I think it was Annex 1 or something. And then the last column, you said it complied with the
Which one?
Yeah, it's a rapid method. Is that right? It is rapid. You get the results immediately.
Sorry,
Is it rapid means immediate results like the biofluorescence type?
Yes.
Okay,
yes.
Thanks,
Which
Yes.
speeds up is much faster because you don't have to wait to incubate the plate, right?
Yeah.
Yeah. Hmm?
Yeah, thanks.
Yeah, the tradition of microbiology has an incubation period, and the essence in combination with rapid methods is our pursuit of something more immediate, something more real time.
Yeah.
Okay, thanks, Kevin. That's okay.
A very quick question. What is the reference air sampler you use for the biological efficiency test? The reference air samplers, yes, Sartorius or a Casella?
The biological efficiency is defined in the ISO 14698 and the EN 17141 guidelines.
The reference air sampler you tested.
Aha, the sampler. So I have shown actually only data related to our instruments. So what we have seen is data for the test sampler MAS 100. Yeah.
Yes, but what was the reference air sampler you use? It is a membrane system with Sartorius or a Casella air samplers?
Yes. I hope I'm not, I will check again and to be sure it's really right, but I think it's the MD8, yeah.
Okay. So Sartorius.
Yes, yeah. I always mix up physical and the biological test, so.
Okay.
Yeah.
Karina Alessia, it was a complicated name, but
no, she's right.
Alessia, you will find her and have a conversation.
Yeah. It should be MD8, yeah.
All right, thank you. Okay, with that we will stop. We'll thank you again, Karina, for your very interesting presentation. Thank you.